Hello and welcome to lesson 1.3, exponential and logarithmic functions. So today we're going to review some exponential and logarithmic functions that we should remember from grade 11. First of all, an exponential function has a parent function usually of y equals a to the exponent x, where a is not equal to 0 or the value of 1, and a is greater than 0. And a is a real number. Its related logarithmic, or also called inverse function, can be described as x equals a to the y, which is not very typical for us to write, because that term has it in terms of the dependent variable compared to the independent variable. The more common version is y equals log to the base a of x. So let's move right along and see what these two functions look like. So we're going to look at the graphs of y equals log to the base 2 of x as an example, and y equals log to the base 2 of x, and how they compare to each other and how you can use them. So we're going to start with y equals 2 to the x, and I'm going to use a table of values to sketch this. Again, if you ever forget how to graph anything, just use a table of values, and it'll give you an idea of what you're looking at. So I'm going to graph this, making note of the y-intercept first. And you'll notice as you go further to the right, values double. As you go further to the left, values decrease by a half. So this is an approximation of what y equals 2 to the x looks like. It has no x-intercept, does have a y-intercept of 0, 1, has a horizontal asymptote of y equals 0, has a domain of all real numbers, or negative infinity to infinity, and a range going only from 0 to infinity. The logarithmic function y equals log to the base 2 of x is the inverse of it, and therefore has a mirror image, the line y equals x. So it looks something like this kind of function right here. And because it's inverse, its properties are similar yet different to that of y equals 2 to the x. So this one has no y-intercept, has an x-intercept of 1, 0, has a vertical asymptote of x equals 0, has a domain of values 0 to infinity, and a range of negative infinity to infinity. As you can see, just the x and y values have been reversed here. So, let's also recall some logarithmic properties. These logarithmic properties help you expand, simplify, or evaluate any logarithms that you may need to do. So an example of the first one would be if you wanted to find out the logarithm of 2 of the value 20. Since most calculators don't have a base 2, you just calculate log 20 and you divide by log 2. The second and third properties can be examined in a similar example together, as they're very similar to each other. So let's say we had log to the base 3 of 4.5 plus log to the base 3 of 6. Each one of these separately are difficult to calculate, but if we multiply them together, this gives you log to the base 3 of the value 27. Well, that is an easier number to work out. And the last one, if you wanted to work out the log to the base 7 of 7 to the exponent 2/5, this is more challenging to work out. However, you can take 2 over 5, bring it out in front, and you can work out log to the base 7 of 7. This is one of the reasons why logarithms were actually created, to make exponential parts of functions actually linear in nature to work out. Log to the base 7 of 7 actually turns out to be 1, so this just remains 2 over 5. So what we can do is use these properties to evaluate these expressions, as if we did not use a calculator. So, assume we can change 8e1 into 3 to some exponent, which we can change it into 3 to the exponent of 4. We can bring the 4 down, log to the base 3 of 3. And again, log to the base 3 of 3 is 1, so this just is 4 times 1, which is 4. Change the 1 over 125 into 5 to some exponent. Well, 5 to the exponent 3 is 125, so 5 to the negative 3 is 1 over 125. Again, we can bring down the negative 3, and this evaluates to negative 3. Okay, so first of all, the cube root of 16 can be rewritten as the cube root of 2 to the exponent 4, because 2 to the 4 is 16. We can now rewrite this as log to the base 2 of 2 to the exponent 4/3, because again, a cubed root can be written as a third of whatever the exponent might be. We can then take the 4/3, bring it out in front, multiply by log to the base 2 of 2, which just changes to 4/3. Okay. You can also use logarithms and exponentials to actually solve equations. So, for example, the first one, we can actually calculate, because they're both exponentials on both sides, we can actually apply a logarithm to both sides. Like so. Then you can bring the x plus 1 down, multiply by log 9, and on the other side the 2x minus 3 comes down, and log of 27. You can then solve this using exact values, or making sure your calculator is always collecting all the exact numbers, and get an actual value for this. I'm going to not solve this, I'm going to let you guys solve it, but I'm going to show you another option that you can use. What you can do is you can change 9 into 3 squared, and you can only do this if you can realize it. If you don't realize it, I'd use the logarithms. And you can change 27 into 3 cubed. If this is the case, you can rearrange this to 2x plus 2 as the exponent, and this one as 6x minus 9. Now that the bases are the same, you can equate the exponents and solve as normal. So this would have been the same solution that you would have gotten from the first expression, just if you made sure to carry all the values properly. For this logarithmic equation, because this is a plus sign right here, and these bases are the same, they're hiding, they're tens, but they're hiding, you can actually combine this into log of x plus 2 times x minus 1. Still equal all to 1. you can simplify that to log of x squared plus x minus 2. Now, in order to get rid of the logarithm on the left side, you change this into an exponential expression or equation. Because the base is 10, you're going to change this into 10 to the 1. Well, we could solve this way. More challenging to solve quadratics like this, so it's probably better to change it to a quadratic that's equal to 0. Again, we can use quadratic formula, or we can factor in order to solve this. So I get two values, -4 and +3. There is only one issue. X equals to -4 is not possible. If you do substitute that back into these original equations, you get a logarithm of a negative number, and that's not possible. Your x values, for the first one, x has to be greater than -2. For our second one, x has to be greater than 1. Therefore, x has to be greater than 1. And the only solution that works then is x equals 3. Okay. You can also use exponential and logarithmic functions to actually solve some problems. So let's suppose Daniel invests $2,500 into an account that pays 2% compounded semi-annually. We want to determine how long until he reaches $4,000. Now this formula you're seeing right here, you might remember, may also be the formula A equals P times 1 plus I to the exponent n. I've seen both being used. It's just in our first equation that I have here, the value of n is actually the number of compound periods and t is the time. Whereas this one is just number of compound periods times time. Okay, so now I'm going to substitute my values in that I know. I know I want to reach $4,000. I know I started with $2,500. My interest rate is 0.02. I'm compounding semi-annually, so 2 times a year. This is going to be 2t. Well, in order to solve this, I need to actually divide both sides by 2,500 first. Probably easier. You could apply a logarithm to both sides first, but I think it might be easier this way. So you get this expression. Now you can apply a logarithm to both sides. Like so. Again, the advantage of a logarithm, it changes any exponential into a multiplication or a linear function, which we can then solve for the value of t here. Oops, wrote that wrong. Taking this, putting it into our calculator, making sure the denominator is in brackets, we get approximately 23.617 as our value. So therefore, this will take about 23.617 years in time. Okay, so moving right along. So how does this help us? Well, as n continues to grow, we can assume that without bound, let's say, so as n approaches infinity, our actual function, 1 plus r over n to the n, actually approaches a specific number. And it's called Eulers number. I know Euler is spelled kind of weird. That's how you spell Euler. This number is a number very close to 3, excuse me, but not exactly 3. We define it as the letter E because Euler invented it. And this value is used as if you were to compound continuously. So the value of E turns out to be approximately 2.718288282459, so forth. It's not an exact number. It's not it's not a rational number. It's an irrational number like pi, and will never end. Euler's number is a number that's really close to 3, somewhere between 2 and 3, and really close to actually 2.72 is even a better option. So we're going to start using Euler's number as well. Thus concludes this lesson 1.3.